Can everybody see the screen and hear me clearly? Hello?
Yes.
Okay. So kindly please concentrate. If you have any doubts, you can stop in the middle and ask me. Okay. So in today's class, we'll be seeing about on the concept called as support vector machines. Okay. So support vector machine is basically a supervised learning algorithm. Okay. So it can be two classes. Okay, it can be used for linear regression or classification, but mainly it is used for classification problems. But it can be used for linear regression also. Okay, regression problems also. Okay, now consider this is class 1, this is class 2. Can you see? This is class 1 and this is class 2. Okay, class 1 and if one can draw a line something like this. Can you see the difference? Something like this. Or I can draw a partition something like this. Can you see the difference? Or I can draw any number of partitions. Can you see, students, how many partitions I've been drawing? Any of these would be fine, but which is the best? Which is the best classifier? Which is the best classifier? That is what we are going to find out. That is what we are going to find out. Okay, we have a line, we have some classes. Okay, some classes. We can either draw this line, or we can either draw a classification line, or a classification line, or a classification line like this, but which is the best classification line? Okay, so now what we are going to do is, how to denote this? We will use a margin as the width of the boundary. Before hitting a data point. Okay. Nearest data point. Okay, one plane will pass through. Okay, can you see one plane is passing through? When this particular passing through, in this example, it is covering 2 data points. Then I draw another parallel hyperplane, okay, on the other side of this particular nearest data point. Okay, for this example, this is only one data point passing. Okay, then I get this margin. Say, for example, I have a classifier something like this, and I have a classifier something like this. Something like this. So what I will do is, I will draw a hyperplane like this. I will draw a hyperplane something like this. Can you see? In this, there are 2 data points passing. In this, there is only 1 data point passing. That is the nearest data point from this point, from the unclassified, from the, say, for example, if this is a negative, I'm just to make you understand, and if this is positive, the nearest data point of the negative and the nearest data point of the positive, okay, I'm passing a hyperplane. And in between these two, I will draw my actual classifier, my actual boundary. So the gap, the entire gap is called as a margin. So support vector machines are the type of supervised learning algorithms that provides analysis of the data for classification and regression. While they can be used for regression, SVM is mainly used for classification. How does SVM works? The basic principle behind the SVM is simple. Create a hyperplane that separates a data set into classes. So create a hyperplane that separates a data set into classes. So it will not only create a hyperplane that separates between two classes, which we have been doing for classification and regression, whatever it is. Apart from that, it creates another two hyperplanes. It creates another two additional hyperplanes, one on each side, such that the other hyperplane pass through the nearest data points. Say, for example, something like this for this example. So for this, something like this example. This is the speciality of the SVM. It does not only create a hyperplane which segregates two classes, but it also creates a hyperplane on the either side of the two classes. So support vector okay. So center line is the hyperplane, which is dividing two classes. Okay, and these two dots, okay, can you see when I'm drawing this line to the nearest data points, and I'm drawing the data point to the nearest data points from this particular hyperplane. Okay, from this hyperplane. So these dots, these connecting data points are called as support vectors. So there are 5 support vectors in this example. Okay, SVM create two marginal lines with some distance, okay, with some distance, so that it is linearly separatable for both the classification points. Okay, now if any data points, say for example, if any data points fall over here, okay, and fall over here in between the classes. For example, this is a cushion. Okay, this is an extra advantage. We can tell that still it belongs to, say, for example, if this is a positive class and if this is a negative class, and if any data points over here, still we can say that this is a positive. This particular point belongs to positive because this is a cushion what we are giving. This is an extra comfort what we are giving. Now, if any data points fall over here, fall over here, fall over here. Okay, then we can say that these points are also negative data points. This is an extra cushion what we are giving. Okay, fine. Now, so it creates a hyperplane, then it finds the best distance. It will create another two hyperplanes on the either side, such that the other planes, okay, will pass to the nearest data points of the positive class, and then another hyperplane will pass through the nearest data point of the negative class. This is the entire functionality of an SVM. This is what makes SVM as SVM. By adding another dimensionality, another two lines to the space, such that this is called as a margin. The distance between the positive hyperplane and the negative hyperplane, including these things, are called as margin. Anything which falls within the margin, inside the margin, if it's a positive class, it will be classified as positive. If it's a negative class, it will be classified as negative. But if the negative class is falling over here, or if the positive class is falling over here, this is a misclassified. Misclassified. If negative class falls over here, it is misclassified. Okay, so this is a positive and this is a negative. Okay. So that is what it is, students. Center line is a hyperplane. SVM creates two marginal lines with some distance so that it is linearly separatable. There will be one more parallel on the either side of the plane, which will pass through the positive and which will pass through the negative points. SVM does not only create one hyperplane, it will create two more hyperplanes, one on each side, such that one hyperplane pass towards the positive and the negative hyperplane pass towards the negative classes. Okay, the distance between the point, okay, this is the Cx point, okay, and the C, negative point C minus, that is the positive and negative, is called as a margin. So we want to create a generalized model to get a better accuracy. Any point which is above this line, can you see above this line is classified as positive. Any classes for this example, okay, you can take either way. Okay, for this example, to have a generalized class, you can take this example and say any point which point towards this line is a positive and this one is a negative. But for this example, I am telling any point which point towards this one. So this is a positive, 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 positive. If I have blue dots over here, again it is positive only. Any point which is falling below this line, below this hyperplane is a negative, is a negative, is a negative. Okay, is a negative. Any blue dot which lies between the hyperplane, can you see? Between the hyperplanes, any blue dots, can you see? Any blue dot which lies between the hyperplane is also classified as positive. Any red dot which falls below this line is also classified as negative only. Is also classified as negative only. Okay, now students, now as I told you, see here, this is considered, this is the positive classes and these are the negative classes. Say for example, so this is the positive classes and this is the negative classes. These are the negative classes. Okay, fine. Now, if I want to draw a hyperplane, I can draw a hyperplane also like this also, right? Okay, and I can divide. Okay, I can draw a hyperplane like this also, and I can divide. But my aim is, okay, I can draw a hyperplane something like this also, I can divide. The point is, I have to take the best possible margin. That is the maximum width where I am getting. I will be considering that particular hyperplane. So if I want to draw, say for example, the distance between, if I draw a straight line like this and a straight line like this, I will get a small margin. Here I will get a large margin. My aim is to maximize the width such that any points, okay, say for example, if my margin is small, the possibility of getting my errors will be more. But if my margin is large, then the possibility of my errors is less. The possibility of errors is less. Here the possibility of the errors is more. So the maximum the margin, the better the width and the better the classifier is. So the better the hyperplane is. You can divide the hyperplane in any way, but you have to take the best large margin. Marginal distance must be maximum such that the errors, the misclassified errors can be there. See, here the possibility is I can have this blue square over here as well as over here. But at the same distance, if I keep the blue square over here and over here, at the same distance, the possibility is here this will be positively correctly classified, but here it is the one misclassified is showing. Why? One reason is why my margin is small. Here my margin is big. My margin is big. Okay, so that's the point we are going for the maximum. I can classify it in any way. Can I say? I can classify it in any way. I can classify it in any way. But my main aim is to have the maximum margin in the support vector. Okay, so if there are two classifiers, okay, something like this and something like this of the same thing, I will go for this classifier because here the margin width is very big, but here also it is classifying. But for a generalized model, think of a generalized model. Think of the many data points which is coming in. But here the possibility of error as you go for larger data sets might become more and more. Okay, so my maximum, my margin, it is should be. Okay, support vector are those points which passes through the planes. So can you see which is the passing through the planes on the either side? So in this example, I have three support vectors on the positive side and two support vectors on the negative side. Okay, and in total five support vectors are there. So in this example, say for example, in this example, another example is five here. Can you see in this example? two support vectors on the positive and one support vector on the negative. In total, three support vectors. Okay. So for example, in this example, if I draw 2 plus 1, 3. Okay. So two support vectors on the positive and one support vector on the negative. One second, students. One second. So the two particular points on the positive in this, okay, two support vectors is passing here and one support, in total three support vectors. Okay, students. Oh, till now everybody is able to understand. Now, what is a support vector? Support vectors are those points. Okay, support vectors are those points which passes to the hyperplanes on the either side. Okay, marginal distance. Okay, we should make sure the distance between these two, including this, is called as a marginal vector, and it should be linearly separatable. When you are doing linearly separatable, make sure, okay, the margin should be maximum width. That is how you need to plot. Is it clear, students? Still here? Is it clear
Sir,
till
I
here?
have a small doubt.
Yes. Yes,
Sir,
please.
if the points are in between the hyperplanes, would they also be considered as support vectors?
No, 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 no. See, once here, initially, I'm starting with this. Initially, I'm starting with this. This is my data point. When you keep adding the data, and if the points come over here. So, for example, these are, so this is my classified. This is my positive classification only. Okay, this is my positive classification. I'll explain you with the help of an example. No worries. Okay. Okay. So now what is happening, students? So what I have done is, since I am not able to put it in the PPT, I have taken the snapshot and I have added in the PPT. Now, students, we have been telling that, okay, now let's consider, okay, now let's consider in this example, consider this is your positive class and this is your negative class. And now I am drawing a plane on the either side, okay, and I have drawn one hyperplane, okay. We will see how I have to draw all these things, okay, fine. So now I am drawing all these things. Now I have a point called as -4, 0 and 4, 4. Okay. Now consider, since it is passing through the origin, I am having the slope as -1. And we know the equation is W transpose T of x plus B, that is mx plus c. Okay. Now we know that m is -1 because our slope is -1. Okay. Now since our slope is this one, okay, the slope is -1. Okay. B is 0. B is 0. Okay. B is 0. Okay. Now, why I am putting W transpose T of x is because I am multiplying. Can you see x? Can you see? So W transpose. So M is -1. M is -1. B is 0. Okay. B is 0. So -1 and 0. And what is the point? Say, for example, I am plotting this particular points. -4, 0. -4, 0. Okay, -4, 0. So this is when I'm trying to multiply two matrices, I need to take transpose. So that is why I'm putting W transpose T. Okay, then what is the value of x? This is x1 and x2. So for example, in this case, it is -4, 0. Now when I'm multiplying, -1 into -4 is +4, positive value, a positive value. So if I take any value, students, can you see? So in this case, I have taken this point somewhere over here, which I'm telling -4, 0, which passes through this point, okay, -4 and on the plane. But if I take any point, students, here, please understand, if I'm taking any point, let it be this point and let it be this point and let it be this point, whatever may be the point, students, whatever may be the point. And if you put it in the place of x, it is always going to give me a positive value. It is always going to give me a positive value. Okay, now let's take this example. Okay, on this side. Now, say for example, let's say for example, this point is 4, 4. This point is 4, 4. Okay, so 4, 4 and -1 and 0. So now when I do the math, I get a negative value. I get a negative value. Now for this point, it is 4, 4. Now if I take any point, students, any point, let it be any point. And if I plot it in the place of this one, now when I try to do a matrix multiplication, I will always get a negative value. So now can I classify this particular diagram? Now can I classify this particular diagram and this particular diagram as one group? which is +1, any point which is lying below this line, I am classifying it as positive, and any point which is above this line, I'm classifying it as negative. Any point is possible as negative. Okay. Now, the same equation, can I write it like this? So this I can write it like, okay, for this equation, I can write it as W transpose X plus B equal to 0. Can you see? W transport X plus B equal to 0. Now, but for this particular line, how can I write like this? So W transpose X plus B, okay, it is always equal to -1 since it's a negative. And for this, I can write it as W transpose X plus B, okay, equal to +1. Can I write it like this? Yes or no, students? So can you see the same? That is what I have written here. Okay, so this middle point I am writing it as 0, and for this line, the equation for this line will be W transpose of X plus B equal to -1. Okay, now when you do the math between -1 and +1, I get this value. I get this value. Now, if I want to remove this transpose, students, okay, I just directly can't remove it. Okay, I need to take a norm of it. I need to take a norm of it and divide by both the sides. So when I divide the norm of it, what happens is I take this, I get this. Okay, I get this. Now I can remove everything. So our aim, students, is to maximize this particular value. Our aim is to maximize 2 divided by norm. That is what I have written. Now, such that how can I maximize this based on a particular condition, such that my W transpose X plus B is greater than 1, greater than or equal to 1, and W transpose B is less than or equal to 1, is less than or equal to 1. Now, this entire equation, can I write it like this? Can I write it like this? How I can write it like this is, now students, now see here, if I take this yi, say for example, this value, if yi is 1, if yi is 1, yi is 1, okay, yi is 1, where is that? Okay. Now we know that, okay, this is the equation for a positive value. We have been know that. But if yi is 1, if yi is 1, okay, so we know that this is the equation, students. Okay, W transpose of X plus equal to 0. Okay, fine. If yi is 1, so 1 into positive value will always give me a positive value. But yi is -1. So for example, if where is that? If yi is -1, if yi is -1, that is this equation, right? That is this equation. That is this part. If yi is -1, -1 into a negative value will always give me a positive value. Will always give me a positive value. That is in both the instances. If it is 1 and this is 1, okay, if yi is 1 into the positive value will always give me a positive value. If yi is -1 into any negative value will always give me a positive value. So I am writing the equation is yi into wt of xi plus bi is always greater than 1. But if it is less than 1, so for example, if it is less than 1, it means that I have misclassified over here. You are supposed to get this equation over here. It should be about this one. For if this value, it should be below this. For if I am using this particular value, but if I get less than 1 means, it means that I have a misclassification. The points are falling over here. But if I'm taking this, and if I get a positive value, say for example, let's take this example itself. Okay. So if I'm doing this math, but instead of positive, if I'm getting a negative, so positive into y, if yi will be 1. So 1 into negative, if I get off negative, it means that these values are falling over here, which is a negative classification, which is a misclassified. The same way, if I'm getting positive over here, and when I multiply yi as -1 into positive, I might get negative. Okay, so it means that I have misclassified over here. That is how I misclassified. It should be always be greater than 1. It means that I have correctly classified. have been correctly classified. So, okay, now students, so this equation I'm writing like this one. Can you see? So this entire equation I can write like this. Okay, so 2 by norm equal to such that y into wy. Okay, having said that, our aim is to students, when you will maximize this is when you minimize this. When you minimize this, this particular entire margin will be maximized. But when you maximize this norm, then the entire margin will be minimized. Okay, so we can, our aim is to minimize this. Okay, our aim is to minimize this such that the entire thing can be maximized. So I can write like minimum of tau of w, the reciprocal of it. Plus I am also having c base I into I power 1 of n to the power of zeta of I. So CI means till how many errors I can go for misclassification. That is, my model can also take, should consider some few types of errors. Okay, so say for example, here my model accuracy is 90% if it's enough. So maximum errors I can have misclassified as 3 also, it's fine on the either side. 3, 3. So, so I am telling that CI, how many errors I can consider. So 4, 5 or 6, how many are misclassified? We need not change our hyperplane. I need not change our hyperplane. Okay, I need not change our hyperplane till if it is 3 or 4 or 5, I am setting the threshold of the error. Okay, and the distance between this and this, the error. Okay, and the summing up. And summing up will give me the total value of the error. The zeta, okay, and the zeta distance between the error values from the point of misclassification. When we sum up, will give me the total errors. Okay, so this is my overall formula. This is my overall formula. Okay, so this part I have written it over here. Okay, now let's solve an example of linear classification. Okay, linear SVM. Okay, linear SVM. Suppose students, we have been given positive label data points. Okay, so 3 comma 1, 3 comma minus 1, 6 comma 1, and 6 comma minus 1, and a negative label data points 1 0 0 1 0 minus 1 1 0. Okay, till now everybody is able to understand. Raise your hands. How many of you are able to understand quickly? I don't have time. Please quickly raise your hands. Okay. Quickly, students. Hello, please quickly raise your hands. I don't have time, students, please. Here, what about others? Here, I will mark you as absent. Either you ask me, tell me, or else you ask me, I will explain you, re-explain you. But if you don't do birth, it's mean that you are not there. Okay, students, now the example is very simple. Kindly concentrate. I will run through it. Kindly listen. If there is any doubt, please do stop me and ask. If you don't stop me and ask, it means that you are able to understand whatever I am teaching. Okay, now suppose students, you have positively labeled data points. So 3, 1, 3 minus 1, 6, 1, 6 minus 1. Negatively labeled, I have given some points. Now I am plotting this in the graph. So 3, 1. Can you see? 3, 1, 3, 1. Then 3 minus 1. 3, 1, 3 minus 1. Okay, 3 1 3 minus, then 6 1 6 minus 1, then 6 1 6 minus 1. Okay, students, now I have plotted this. Then negatively labeled data points 1 0 0 1. So 1 0. Okay, then 0 1. Okay, 0 minus 1 0 minus 1 minus 1 0 minus 1 0. So I have plotted the points. Okay, now having said that, okay, now 3 support vectors I have got. Okay, now what are the 3 support vectors? Which is the nearest data points? And you see, this is one nearest data point, and these two are passing through the same line. So that means I have to draw 2 hyperplanes, right? 2 hyperplanes. This is one hyperplane, and this one hyperplane. Right now, I am not drawing the hyperplane, but this is just to make you understand now which type of hyperplane I will be drawing, that we will be discussing in the end. Okay, fine. So these are the 2 nearest data points. Okay, where can the hyperplane pass? Okay, so it is 1 0, 3 minus 1, and 3 1. So this is my, these two are my positively labeled. Let's say, for example, positively labeled positively labeled because this belongs to the, it is given, right, positive classes. Okay, and this is my negative. So I have three total support vectors for this example, three total support vectors for this example. If there is another plane passing through this, then I will have four support vectors. But for this example, I have only three support vectors. Okay, so this is one, this is one, and this is one. So 1, 0, 3, 1, and 3 minus 1. So 1, 0, 3, 1, and 3 minus 1. So S1, S2, and S3, out of which this is the negative and these two are the positive. These two are the positive. Okay. Can you see? This is the negative and these two are the positive hyperplanes. Okay, fine. So then after calculating the support vectors, I am going to add a bias to it. Bias input is or should be added up. Okay, so bias, because the probability is everybody can be a zero, like how we have did in Adeline, how we have did in this one. The same way we are going to get it. What will happen if everybody gets zero? So the bias will play an important part. So I'm adding a bias always as one. Okay, so 1, 0. Can you see? Now I'm adding a bias 1, 1, 1. Okay, so that is what I have written here. 1, 1, 1. So that when I am adding a bias, it is called as S1 tilt, S2 tilt, and S3 tilt. Okay, S1 tilt, S2 tilt, and S3 tilt with the bias value. Okay, now after having the bias, since there are one negative and two positive, kindly please remember this is a dynamic equation. This will change accordingly. So for this example, how many negative classes are there? One negative classes are there, one negative classes are there, and two positive classes are there. Okay, so now first we will write the equation with respect to this, then with respect to this, and then with respect to this. Now if you have another negative classes, then you need to add another equation here also, like that the entire equation will expand. So there is a dynamic equation. So for this class, so alpha 1 into S1 of tilt. Okay, S1, can you see S1? Because we are classifying it with respect to the negative class, the first one, negative class. Then alpha 2 S2 with respect to negative class, and alpha 3 S3 with respect to negative class. Then these two are the positive classes. Okay, so alpha 1 S1 with respect to the second support vector positive class, alpha 2 S2 with the second support vector positive class. Okay, and the alpha 3 S3 with second to the support vector 2 with the positive class. Okay, alpha 1 S1 with support to the third vector positive class, alpha 2 S2 support to the third vector positive class, and alpha 3 S3 with support to positive class. Now replace this equation. Okay, so alpha is S1 is what we have calculated, right? S1 tilt, S2 tilt, and S3 tilt we have been calculating. So 101 into 101. Then 2 we know. Okay, see, it just plug in the values. Just plug in the values. Okay, equal to -1. Then plug in the values equal to 1. Then plug in the values. So you will get this one. See, 1 plus 1, 2. Okay, 0 and 2. Okay, so 1 into 1 and 1 into 1, which is 2. So 3 into 1, which is 3, and 1. So 3 plus 1 is 4. 3 into 1 is 3 and 4. The same way, 3 and 4. 3 threes are 9, 10, 11. Okay, 3 threes are 9, 9. This and this will get cancelled. That's all. The same way. Okay, so 3 threes are 9. This and this will get cancelled. 3 threes are 9, 9, and 10, 11. So 3 ones are 3, 3, 4. So you get this value. Now when you solve it, you get alpha 1, alpha 2, alpha 3. Okay, students, alpha 1, alpha 2, alpha 3. Now, having computed alpha 1, alpha 2, and alpha 3, we are going to calculate the weight vectors. Okay, calculating the weight vectors. Weight vectors is given by the formula, okay, alpha I into Si of tilt, where I represents the particular value, the number of support vectors. The number of support vectors. In this case, how many support vectors? It is 3 support vectors. So alpha 1 S1 plus alpha 2 S2 plus alpha 3 S3. So what is alpha 1 value? What is alpha 1 value? We have calculated minus 3.5 into S1. What is S1 value? We have calculated here. The same day, alpha 2 value S2, alpha 3 S3, alpha 2 alpha 3, alpha 2 alpha 3, then S2 and S3. So when you do the math, I get this one. Okay, I get this one 102. Now out of this 102, 1 and 0 are the actual weight vectors. Okay, 1 and 0 are the actual weight vectors. And this 2, what we have added here as a bias. Can you see, students? We have added as a bias here. Now we are segregating this. Okay, now we are adding here. Now in this step, we are segregating this. Segregating this. So that is what it is. These are the actual weight vectors, and this is the offset, which is otherwise called as a bias. So 1 and 0, whatever we are getting, we are aggregating 1 and 0, and the 2 as the bias. Okay, now the equation of the hyperplane is Wx plus p. Now the weights are 1 and 0. Kindly please remember, okay, 1, if I get the weight 1 and 0 means I will draw a straight line with respect to the y-axis. A straight line, parallel line, sorry, a parallel line with respect to y-axis. Okay, but if I get 0, 1, I will draw a parallel line with respect to x-axis. But if I get 1, 1, if I get the vector as 1, 1, I will draw a 45-degree angle. Right. So 1, 0 means a parallel line with respect to y-axis. 0, 1 means a parallel line with respect to x-axis, and 1, 1 means a 45-degree line. It can be like this, it can be like this, depending upon. Okay, now b equal to minus 2 means, it means that b equals to plus 2. And when b equals to, if I get plus 2 means, I will draw b equals to minus 2 in the quadrant. Okay, when you substitute this. Okay, students, what have we got, students? 1, 0, and b equals to minus 2. Minus 2 means, okay, minus 2 means, kindly please understand. Okay, so 1, 0 means, first you need to understand which line I'm going to draw. Okay, so this is my y-axis, this is my x-axis. Okay, this is my y-axis and this is my x-axis. So 1, 0 means I will be drawing a parallel line with respect to y-axis. Okay, y-axis. Now at which point I will draw? I will draw where b equal to the minus 2 we have got, right? So minus 2 means I will draw in the plus 2 quadrant. But in case if I have got b equal to 2 means I will be drawing somewhere over here in the minus 2 quadrant. It is something like b equal to minus 2. Okay, when you do this, you get b equal to 2. So only I'm drawing at b equals to 2 here. Okay, so when you get b equals to plus 2 means equal to 0 means b equal to minus 2. Minus 2. So since I have got minus means plus, plus means minus, students. Remember this, that's enough for you people. Okay, so since I have got 1, 0 means I know that I have to draw here. At which point I have to draw? At which point I have to draw? I have to draw at point 2, that 2 in the second quadrant, that is in the positive plane. So I am drawing this one. So this is my best margin dividing plane. This is my another margin, you can say, and this is my another margin you can take for this line. This is my best possibility for this particular data points, because I can't draw a margin like this, right? I can't draw a margin like this. I can't draw. Okay, which because my width will not be there. So this is my best margin for the given data sets. This is all about linear. This is all about linear. Have you people understood? How many of you are able to understand? Quickly raise your hands. Quickly raise your hands. Quickly raise your hands. Okay, students. Okay, now I will move on to non-linear SVM. Okay, so now what is non-linear SVM? So non-linear SVM means, say for example, if my data points are something like this, and if my data points are something like this. Okay, how can I classify? How can I classify? Okay, so when this type of a thing is done, it's called as a non-linear data set. So you people know, right? You people have done so much of linear and non-linear. So for non-linear, we have to convert this particular points from 2D, from one dimension to another dimension. That is from one feature space to another feature space to another feature space. Okay, that is from one dimension to another higher dimension. Okay, then I can apply, then I can go ahead and apply the linear rule. Okay, so first let us consider, okay, so now let us consider a positively labeled data points and the negative labeled data points. Now let me plot first. That is, okay, 2 2, can you see? 2 2, 2 2, 2 2, then 2 minus 2. Okay, then minus 2 minus 2. Okay, and minus 2, 2. This is minus 2, 2. Okay, so this is 2, 2, 2 minus 2. Okay, minus 2 minus 2. Okay, and minus 2 and 2. So this is the positively labeled. Negatively labeled means what? 1, 1. Okay, 1, 1. 1 minus 1. Minus 1 minus 1 and minus 1 1. Okay, can you see, can you do a segregation on this? Can you do a segregation on this? Because it is non-linear, it is not possible to classify it. So what we do is we are going to convert this one dimension to another dimension. Okay, so from one dimension to another dimension. So our goal is to discover a separately hyperplane that can accurately discriminate. It is obvious that no such hyperplane can exist in the given input space. So there we must use a non-linear SVM where whose mapping function is a non-linear mapping from an input space towards some other feature space. Okay, so the conversion happens, okay, using this particular formula. Very simple, students. The conversion happens between from converting from one space to another space. Converting from one dimension to another dimension happens based on this condition. Okay, if this condition is satisfied, you will apply the formula in this rule and then you will generate the points of x1 and x2. If the condition fails, you will keep the points as it is. That's all, students. That's all. Okay, now let's take the first one, 2, 2. So 2 squared plus 2 squared is what? 4 plus 4. So square root of 8 is greater than 2. Yes, it satisfies. So what I do is x2 is 2, x1 is 2, x2 is 2. So 2 minus 2 is 0. Then 4 minus 2 is 2. So I get 2. Then the next point. Okay, then the next point. Then the next value. So 2 minus 2. So 2. Okay, then I get x2. 2. Okay, then I will just solve it for here till here, then you can see. Okay, then the next part. Okay, so then the next part, 2 and minus 2. So 2 squared 4, 2 squared 4. So square root of 8 greater than 2. So again 2, 2. Again I get, see, 2, this is 2 and this is minus 2. Can you see? This is 2 and this is minus 2. So 2 minus of minus 2. So 2 minus of minus 2 is 4. So minus of minus 2. Okay, so minus of minus 2. So 4 plus 2 is 8. Okay, so 4, 2 plus 2 plus 2 plus 4. 4, 5, 6, 7, 8, 9, 10. 9, 10. The same way, 2, this is for this one. Okay, so then you plug in all the values and you see. You try it out. Okay, so 10, then you see, you try it out. So you will get all these points. Will get out these points. But here, if you see the another one, if you see, so 1 squared plus 1 squared square root of 2. Okay, it is not satisfying. So x1 and x2 remains the same. So all the conditions here are not satisfying. So you will keep it as it is. You will keep it as it is. Now what you will do, you will plot the data points. Now you will plot the data points. Can you see? 2 comma 2, 2 comma 2. Okay, then 10 comma 6, then 10 comma 6, 6, 6 comma 6, then 6 comma 10, then 6 comma 10. Okay, then this is the same data points. The 1 1 1 minus 1, can you see? This is 1 1 1 minus 1. Okay, now which are the two nearest vectors? Now which are the two nearest vectors, students? For this one, how many support vectors are there? How many support vectors are there? Just by seeing, it is 1 and it is 2. There are two support vectors, right? This is 1 comma, that is 0 comma 1 and 2 comma, sorry, 1 comma 1. Okay, and 2 comma 1. Can you see? These are the two support vectors. So 1 comma 1. Can you see? 1 comma 1 and 2 comma 1 and 2 comma, sorry, 2 comma 2. 2 comma 2. 1 comma 1 and 2 comma 2. Now, since you have got it, now the same process of linear, students. Now from here, the same process of linear. No change at all from here. Okay, so the initial step only, convert them from one dimension to another dimension. You get the data points, you plot, you take the support vector. Now it's the same process. Now add a bias, 1 1 1 2 2 1. So now apply the same equation. Okay, here this time it is only one negative. Negative, can you see? This is a negative classified and this is a positive classified, right? Negative classified and positive classified. So one negative and one positive. So alpha 1 S1 into this one alpha 1. So now plug in the values. You get the values of alpha. We get the values of alpha. Put it in alpha where I is the number of support vectors. In this case, it's 2. Now, see, you are getting 1, 1 and the bias is -3. So 1, 1 means, what did I tell you, students? What did I tell you? 1, 1 means what type of line? What type of line? 1, 1 means what type of line, students? You will get? Hello?
45-degree.
45-degree line. Okay. And with the -3 means +3. Okay. So can you see +3 and it is passing through +3 and it is passing through +3 quadrant. A 45-degree. Whatever may be the degree, you cross it. Okay, so this is how you will be using linear SVM and non-linear SVM. Is it fine to you, students, everybody? Linear and non-linear?
Yes, I understood.